and welcome to a new video on IGCSE Classified Paper 2 Physics. In this video, we shall be discussing the law PV equals KT. We shall begin with introductory concepts that lead us up to the law, and we shall begin with the relationship between temperature and the speed of molecules in a body. The gas is stored in a sealed container of constant volume. The temperature of the gas increases. This causes the pressure of the gas to increase. What happens to the gas molecules during this pressure increase? So the main concept we want to discuss in this part is that when the temperature of a gas increases, the average kinetic energy of its molecules increases, and therefore the average speed of the molecules increases. So in this question, the correct answer would be choice A. The average kinetic energy of the molecules increases. A cylinder containing trapped air is put into a freezer. As the air cools, the piston moves to the left as shown. How has the air changed? Like we said, the higher the temperature, the higher the kinetic energy, and the higher the speed. So the reverse argument also works. If you put it in a freezer, then the temperature will decrease, the kinetic energy will decrease, and the average speed of the molecules will decrease. So the correct choice here is choice C. A sealed bottle of constant volume contains air. The air in the bottle is heated by the sun. What is the effect on the average speed of the air molecules and the average distance between them? So this is important. First of all, like we said, if something is heated, its temperature increases, so the average speed of the molecules increases. But what's confusing here is that most people will probably choose to go with C, because as the speed increases, they imagine that the distance between the molecules increases as well. But this is incorrect. Why is that the case? Because if we have a bottle and we have gas molecules in the bottle, we should know that the gas molecules are randomly spread about in the bottle. They take the shape of the container and the volume of the container. So they occupy the entire space and they're constantly moving about, right? So what happens if we heat up the bottle? Well, they will start moving faster, but in the end, they will still be within the same distance from each other because they were already occupying the entire bottle. Think of it this way. You have four molecules, sort of like four balls, four very small balls, for example, in this rectangular box, right? And they're randomly spread about. So what is the distance between them? The distance between them is roughly this amount, right? And then they're going to start moving about. So let's say this ball comes here and then this ball goes there. So what is the new distance? It's roughly still the same amount. So they'll keep moving and they'll end up in random positions, but the distance between any two molecules doesn't really change because they already occupied the entire volume of the bottle. So the correct choice here is choice D. The speed, increases and the distance stays the same. So D is the correct choice. Next, we analyze the effect of this increase in speed that we talked about on the walls of the bottle or the container in which the gas molecules are. So gas molecules striking a container wall cause a pressure to be exerted on the wall. Which statement explains this? So here is the thing. Like we said before, let's go back to the example of the bottle. We have an empty bottle and there are gas molecules inside the bottle. And we heat the bottle up. What happens to the gas molecules? We said they move with greater speeds. So when they move with greater speeds, they collide with the walls of the container with greater speeds. And from mechanics, you should know that greater speed means greater momentum. What is momentum? Momentum can be expressed as P or M or whatever. P is equal to the mass times the velocity of an object. This has to do more with mechanics, but it's relevant here. So as the speed of the molecules increases, their momentum increases. So what happens when they collide with the wall at a greater momentum? Well, as the momentum increases, after the collision, the impulse increases as well. And there is an equation for impulse. Impulse equals force times time. So the force increases as well. So let's recap. When the velocity increases, the momentum increases. So the impulse on collision with the wall increases. So the force increases. And that's what we care about for the purpose of this problem. What happens when the force increases? Well, we should know that pressure is equal to force over area. So as the force increases, the pressure also increases. Watch out, because this P stands for pressure and this P here stands for momentum. Maybe we can just change it to M so as not to confuse you. This is momentum. Right? So the idea is that when we heat an empty bottle, for example, that only contains gas molecules, the speed increases of the molecules. So the momentum increases, so the impulse increases, so the force increases, so the pressure increases. This is the long answer to the question. But for the purpose of this question, we just need to understand that when a molecule rebounds, there must be a change in its momentum. This is the idea of impulse. Change in momentum is the idea of impulse, and this is what causes the pressure. So the correct choice here is B. A car tire has constant volume. Why does the pressure of the air in the tire increase when its temperature increases? Again, this is the same idea. Temperature increases, so velocity increases, so momentum increases, so impulse increases, force increases, and therefore pressure increases. So why do I insist on writing this very long chain, even though the answer probably doesn't require it? I just want to prepare you for paper 4, because in paper 4, you might get this exact same question for worth 4 or 5 marks, and then you need to describe this chain as it is. For the purpose of this question, A and B, of course, are wrong. B would have been A is completely irrelevant anyway. We don't care about the molecules hitting each other. We care about the molecules hitting the walls of the container. And B is wrong because it should have been more often, not less often. So two things happen when the speed increases. The molecules hit harder with a greater momentum, and they also hit the walls more often. So you have more collisions. And this again contributes to pressure, of course, using the same logic. But B is wrong because they said less often, so this is incorrect. The average speed of the air molecules in the tire is greater. Yes, this is correct. There are more air molecules in the tire. No, this is wrong. Where would the air molecules come from? This is a car tire that is closed in and of itself, and there are a certain number of air molecules inside it, and that does not change when we heat the tire. So the correct choice here is C. So here they're just talking about this part of the equation. As you might remember from the previous question, we reached up to here. Different questions might tackle different parts of the chain. So anyway, C is the correct answer. A gas at constant temperature is in a container of fixed volume. The gas exerts a pressure on the walls of the container. The pressure is caused by the gas molecules striking the walls. This is what we're talking about, momentum and impulse and so on. Which statement about the gas molecules when they strike the walls is correct? So the average kinetic energy changes, the average momentum changes, the average speed changes, or the chemical energy changes. Of course, when we're talking about collisions and striking the wall, we're going to go with B, the average momentum of the gas molecules changes. So B is the correct answer. The diagram shows an air-filled rubber toy. Child sits on the toy and its volume decreases. The temperature of the air in the toy does not change. How does the air pressure in the toy change and why? So there is no temperature change here. So the speed of the molecules does not really increase. However, the volume decreased. So instead of having, for example, this container containing the 4 molecules, as in the previous example, we crumpled the bottle in a sense. Let's say it's a plastic bottle, and we kept squeezing it until it crumpled and it became half or maybe 60% of the original volume. And we still have the 4 balls. We did not increase the temperature or anything, so they're still moving with the same speed. But what happens? Well, if the volume is smaller, then they will collide more often with the walls because the volume is now smaller. So there are increased collisions with the walls of the container. And this will lead to an increase in pressure. So the correct choice here is D. The pressure increases because the air molecules strike the rubber more frequently. This has all been meaning to lead us to this very important equation, PV equals KT. K here is a constant, so it's not something we really care about for now, but we just care about this relationship, PV equals T. I'm going to take this opportunity and I'm going to describe the relationship between P and V and T physically and mathematically. So let's start with the mathematical part. P times V equals T, right? So let's keep T as a constant. Let's say T equals to 10, for example. So I'm just going to keep the temperature here as 10. What happens if I put the pressure as 1? What happens if I put the pressure as 2? What happens if I put the pressure as 5? So if the pressure is 1, the volume must be 10 because 1 times 10 equals 10. If the pressure is 2, then the volume is 5. If the pressure is 5, then the volume is 2. So what does this tell me? This tells me that if this is constant, then these two must follow an inverse relationship. And this works for any equation, not necessarily pressure and volume. This mathematical representation tells us that if we have two variables on the same side equal something else, and we keep this other third item constant, then these two have to follow an inverse relationship, which means that as pressure increases, volume decreases and vice versa. If pressure decreases, then volume increases. Now, let's try to keep something else as a constant. So let me try this again. Okay, excuse me. So we've said so far that as pressure increases, volume decreases. Now let's try keeping the pressure constant. We said we have K, but we said we don't care really about K, all right? So P times V equals T. Now let's try keeping the pressure constant. I'm just going to keep the pressure at 2, for example. And I'm going to change the values of V and see what happens. So 2 times, let's say 1, 2, and 3. Let's observe what happens to T. So here, 2 times 1 equals 2, 2 times 2 equals 4, 2 times 3 equals 6. So the relationship between these two quantities is direct. As the volume increases, the temperature increases. We don't really care about the physical interpretation. We don't care about physics right now. I'm just telling you the way to analyze this mathematically. As one of them increases, so does the other. So V and T are directly proportional. Now let's try to do the other way around. Let's keep the volume constant. So let's keep this as 2. And let's maybe try to change the pressure. 1, 2, 3. So you get you get 2, 4, 6 as well. So in this case as well, the pressure and the volume have a direct relationship. As pressure increases, as pressure increases, volume increases, and vice versa. So we've done this mathematically. We've found relationships between each two quantities mathematically. And the summary is, for the quantities that are close to each other on the same side of the equal sign, the relationship is inverse. It's an inverse relationship. But for any quantity on the left compared to any quantity on the right, the relationship is direct. And this applies to any equation of the form AB equals C. Just by looking at it, you can automatically infer that as A increases, C increases, as B increases, C increases, but as A increases, B decreases. So that's the only inverse relationship there is. This is an important skill to learn to analyze any equation you ever meet. Now, let's talk about this physically. We want to explain these three relationships from a physical perspective. So what happens? What is the relationship between pressure and volume? Let's go back to the bottle. Like we said, if I have this bottle with the 4 balls, and in this case, I don't care about the temperature. The temperature is constant. We don't care about the temperature. I'm just going to shrink the bottle, maintaining the 4 balls inside, the 4 molecules in a sense. So what happens? Like we said, since the volume is smaller, the molecules collide with the walls more frequently. Therefore, the pressure increases. So this justifies this relationship. As the volume decreases, the pressure increases. What about volume and temperature? Well, if there is no effect on the pressure, if we're keeping the pressure constant, if we don't care about the pressure, things tend to expand when they're heated, right? Ever so slightly, but like if you have a sort of a metal box like this and you heat it up, it's going to get slightly large. That differs depending on the material of the metal and so on, but like this is a simple relationship to explain. If I heat something up, it expands, assuming no change in pressure. Now let's move to the third one. Oh, excuse me, I made a mistake here. This is not P and V, this is P and T. We already mentioned P and V. I'm sorry about that. This is P and T. So what is the relationship between pressure and temperature? This one is the one we've been discussing for the most part of this video. I have a bottle with 4 molecules, and now I heat it up. I don't change the volume at all. It's the same exact bottle. What happens when I heat the bottle up? The molecules move faster. They strike the walls harder and more often due to the increased kinetic energy, which leads to greater velocity, greater momentum, greater impulse, greater force, and so on, like we talked about, the chain we talked about. So when I heat an empty bottle up, the gas molecules inside it strike the walls more often and with greater momentum and force, and this leads to more pressure. So this explains the third relationship, which is the relationship between pressure and temperature. So sorry I've taken some time outlining all of this, but it's important to visualize from a mathematical perspective as well as from a physical perspective. Let's move on to the questions then. The diagram shows a quantity of gas enclosed in a cylinder by a piston. The piston is moved to the left or to the right. The temperature of the gas is kept constant. So this is very important. Let's always start with the equation PV equals KT. We don't really care about the K. I have to write it just for correctness, but K doesn't really affect our problems in any way. So for now, we can just ignore the K. So the temperature is kept constant, so we don't really care about the T as well. So what is the relationship between P and V? We said if they're on the same side, as pressure increases, volume decreases, and vice versa. So they have an inverse relationship. So which row describes the effect of moving the piston slowly in the direction shown? So bear in mind that if it moves to the left, that means that the volume decreases, right? So let's just add a column for volume here. Volume decreases, volume decreases, volume increases, volume increases. And this is common sense. If you move this to the right, you're giving more space for the gas. You have more volume. So left means that the volume decreases and right means the volume increases. Let's talk about pressure. We said that pressure and volume have an inverse relationship. So decreases should be increases here, right? So this is wrong. This is definitely wrong. Here we have decreases and increases, so this could be correct. Here we have increases and decreases, so this could be correct. Here we have increases and increases, so this is definitely wrong. Now we need to figure out whether it's B or C. B and C are correct in terms of the movement and the pressure, but we need to figure out the speed. What happens to the speed? Of course, since the temperature does not change, then the speed does not change as well. So there's no change in the speed. So therefore, B here would be the correct answer. Air is trapped in a cylinder by a piston. The original volume is V and the original pressure is P. The piston is pushed to the left. The temperature does not change. So let's write down our equation. PV equals T. We're ignoring the K, and here we're ignoring the T as well because the temperature does not change. So the relationship between pressure and volume is an inverse relation. Now, the piston moved from 50 to 25. So what happened to the volume? The volume became halved. It reduced by half. So it became V over 2. We divide the volume by 2. So therefore, because the pressure is the inverse of the volume, we must multiply the pressure by 2 to counter effect the division of the volume. It's the opposite process. So we go with choice D, V over 2 and 2P. How did we know that it's V over 2? Because 50 divided by 2 gives us 25. So the correct choice here is D. A diver underwater using breathing apparatus at a depth where the pressure is so and so. A bubble of gas breathed out by the diver has a volume of 20 when it's released. The bubble moves upwards to the surface of the water. At the surface of the water, the atmospheric pressure is 1 times 10 to the power of 5. The temperature is the same. What is the volume of this bubble when it reaches the surface? So let's start with the equation. PV equals KT, but we don't care about the K, like I said. Let's just assume it's equal T for now. And the temperature of the water is the same. So since the temperature of the water is the same, we don't even care about the temperature. So PV equals some sort of constant then. How does that help us? It means that the pressure times the volume has the same answer throughout the problem. So we have 2 different pressures here. So another way of writing this equation would be P1 V1 equals P2 V2. And that tells us that for any point, the pressure times the volume is the same. We can even say equals P3 V3 equals P4 V4 and so on. At any point, the product of pressure and volume is the same. So what 2 points do we have here? We have where the diver is, so we have the surface and we have the diver. We have point D and we have point S. Point D is at the bottom and point S is on the surface. On the surface, we have atmospheric pressure. So let's call the point D point 1 and let's call S point 2. So for S, for point 2, we have atmospheric pressure. So I can write, instead of P2, I can write the atmospheric pressure, which is 1 times 10 to the power of 5. And where the diver is, the pressure is 1.25 times 10 to the power 5. So I can write that instead of P1. And what about the volume? The bubble breathed out by the diver has a volume of 20. So this volume relates to the diver. So relates to 1. So I'm going to remove V1 and I'm going to write 20. And equals, I'm sorry, they're not exactly on the same level. Let me try to fix that. And obviously we need to find V2, which is the volume of the bubble at the surface. So how do we find V2? This is mathematical. So V2 equals 1.25 times 10 power 5 times 20 divided by 1 times 10 power 5. And you simplify. So these are cancelled out. 1.25 times 20, that gives us 25. So the correct answer here for V2 would be 25 centimeters cubed. The diagram shows a gas is trapped in a cylinder by a piston. The volume of the gas is 120 and the pressure is P. The piston is moved slowly to the left so that the volume is reduced to 30. The temperature does not change. So when we have multiple pressures and multiple volumes and so on, especially if the temperature is constant, so PV equals T and we remove the T, it's constant. So we can just say P1 V1 equals P2 V2. Now, what quantities do we have? We have that the initial volume is 120. So this is 120. And we have the initial pressure as P. For the final state, the volume is 30. And we want to find P2, the final pressure or the new pressure. So P2 equals P times 120 over 30. And you simplify, so you get 4P. Therefore, the correct choice here would be choice D, 4P. The volume of a gas is measured at different pressures. The pressure P and the volume V are found to be related by the equation PV equals constant. Which quantities are kept constant and which quantities changed? So PV equals constant means that the temperature is constant. So this is wrong. So it's one of these three. What about the mass? We've never ever mentioned anything about changing mass, right? So obviously these are wrong and the correct choice is C. What about density? Should density change? Yes, density should change. Why? Because the volume is changing. So if the mass is the same and the volume is changing, that means that the density must change as well because rho equals mass over volume. So if this guy is constant, because the mass is always constant, and the volume increases, for example, then the density will automatically decrease. So the only thing changing here is the density. So C is the correct answer. The pressure of a fixed mass of gas in a cylinder is measured. The temperature of the gas is then slowly increased and the volume does not change. Which graph shows the pressure of the gas during this process? So let's start with our equation. PV equals KT or equals T. K is a constant anyway. In this case, the volume does not change. So let's cross out the volume. What is the relationship between pressure and temperature? If you remember our mathematical analysis, we said that if they're on opposite sides, they have a direct relationship. So pressure and temperature have a direct relationship. So if the temperature is slowly increased, then the pressure is slowly increased as well. So do you think we should go with B or C? Because obviously we know that the pressure is increasing, so it's not A and it's not D. Do you think we should go with B or C? Well, the pressure is never zero, right? Because especially that they told you that the pressure of a fixed mass of gas is measured. So you're measuring something, obviously it's not zero. And physically, you can't imagine really zero pressure. That means that the molecules are not moving at all. There are no collisions whatsoever. So it does not start at zero, definitely. So since it does not start at zero, therefore the correct answer is C. A cylinder of constant volume contains a fixed mass of gas. The gas is cooled. What happens to the pressure of the gas and what happens to the kinetic energy of the gas molecules? Like we said, if the gas is cooled, then the kinetic energy definitely decreases. So we don't want anything to do with B or D. What about the pressure? Let's go back to PV equals KT. So constant volume, so we don't care about the volume, we don't care about the K. So the relationship between P and T is direct. So if the gas is cooled, then the temperature is decreasing, so the pressure is decreasing as well. So A would be the correct answer here. And this brings us to the end of our video. Thank you for watching. I hope this was beneficial to you.